Large-scale heat pumps and decarbonization, a quick overview comprehensive resource on heat pump technology prepared by Selva Calixto in the quest for sustainable and efficient heating solutions. Large heat pumps have emerged as a key technology with the potential to decarbonize the buildings, district heating, and industry sectors.
What you are about to discover in the next minutes. How does a heat pump work? What kind of sources can be harnessed thanks to this technology? Which sectors could benefit from the use of large heat pumps? A real-world example. Understanding heat pumps. Heat pumps are devices that utilize the principles of thermodynamics to transfer heat from one location to another. They operate on a closed-loop cycle similar to a refrigerator, extracting heat from a low-temperature source and releasing it at a higher temperature. The key components of a heat pump system typically include evaporator. This is where the heat pump absorbs heat from a low-temperature source, such as the environment, water, or the ground. The working fluid, often a refrigerant, evaporates in this process. Compressor. The vaporized refrigerant is then compressed, raising its temperature and pressure. This compression process requires energy input and is a crucial step in the heat pump cycle. Condenser. In the condenser, the high-temperature, high-pressure refrigerant releases heat to the district heating system or space to be heated. This heat transfer is what provides warmth to buildings or hot water for various applications. Expansion valve. After releasing heat in the condenser, the refrigerant passes through an expansion valve, where its pressure and temperature drop significantly. This prepares it to return to the evaporator and start the cycle again. Heat pumps come in different types, each designed for buildings, districts, or industries. What types of sources can this technology harness? The diagram illustrates the operational principles of heat pumps in the context of district heating and industrial applications. It showcases the various stages of heat pump operation and the different sources and sinks involved in the process. Heat sources. The top part of the diagram identifies possible environmental heat sources that large heat pumps can exploit. Air. Heat pumps can utilize ambient air as a heat source, with their performance subject to the impact of daily and seasonal temperature variations. Water. Surface water or groundwater can provide thermal energy for heat pumps, often offering a more stable temperature profile than air. Ground. Heat from the earth can be tapped for its relatively constant temperature, which is beneficial for heat pumps. Waste heat. Industrial or urban, waste heat can be recovered by heat pumps, contributing to higher system efficiency. The middle section of the diagram describes the thermodynamic cycle of a heat pump: evaporation, compression, condensation, and expansion. This cycle is powered by electricity, as indicated by the yellow arrows. Heat sinks. The heat extracted from the sources and upgraded by the heat pump can be delivered to various sinks. Air. Heat can be distributed via air for space heating. Water. Hot water distribution. For residential or commercial building heating. Steam. Industrial processes often require steam, which can be generated by heat pumps. Heated material. Some industrial processes may use direct heated material from heat pumps. Which sectors could benefit from the use of heat pumps? Buildings. Providing space heating and hot water. District heating. Centralized production of heat distributed across a network for residential and commercial buildings. Industry. Unlike those used in buildings, industrial heat pumps operate at higher input temperatures to achieve the necessary higher output temperatures for industrial applications. Heat pumps function as a sustainable technology, utilizing low-grade heat from various sources and upgrading it for heating purposes in a range of applications. The ability to integrate with waste heat recovery also illustrates the role of large heat pumps in circular energy systems. A real-world example: the Arc Gentilly geothermal project in France. The Arc Gentilly district heating project launched between 2014 and 2015. This ambitious initiative has tapped into a deep geothermal source located 1,500 meters underground, with water temperatures reaching 60 degrees C. The project successfully supplies heat at 70-75 to approximately 10,000 households, translating to an impressive 100 gigawatt per year in energy production. What makes this project particularly noteworthy is the exceptional coefficient of performance that can reach between 7 to 9, highlighting the system's high efficiency. However, such groundbreaking projects do face challenges, primarily the substantial upfront costs. To overcome these barriers, the Arcel Gentili initiative has benefited from several financial incentives. Long-term contracts of a minimum of 30 years, facilitating the amortization of the capital expenditure, CAPEX. Subsidies accounting for 23% of the CAPEX, significantly lowering the initial investment hurdle. A reduced value-added tax, VAT, from the standard 20% to 5%, easing the financial burden further. The introduction of white certificates in 2022, which recognize the efficiency of district heating systems that utilize over 50% of renewable energy sources. In the wake of a dramatic increase in gas prices in 2022, the Arcel Gentili geothermal heating system has emerged as an even more attractive and cost-effective alternative compared to traditional systems reliant on fossil fuels. For a more in-depth look at this groundbreaking project, watch the detailed YouTube video.
If you found the insights shared in this article thought-provoking and wish to delve deeper into this critical subject, I invite you to join our community dedicated to advancing sustainable heating systems. By subscribing to our mailing list, not only will you receive updates and exclusive in-depth content directly to your inbox, but you will also gain early access to my first upcoming ebook on sustainable heating systems.